This is Dr. Furushani, and in this video, I'm going to show you how to run multiple linear regression analysis. Imagine that we have two independent variables that I call them as IV1 and IV2, and one dependent variable that I call it as DV. And my research question or hypothesis is that how these two independent variables can predict this dependent variable and whether uh, the effect is in a positive direction or negative direction. That means that I want to see if higher levels of these variables can be significantly predicting lower levels of my dependent variables, or can be in opposite direction. Can be like higher levels of these variables can predict higher levels of my dependent variables. So for these types of research question or hypotheses, we can run a multiple linear regression analysis. Multiple because we have two independent variables, or we could run the same analysis if we had more. And also you can run the same type of analysis if you just have one independent variables, and the outputs and most of the assumptions would be the same. So the good point for multiple linear regression analysis in SPSS is that you can run both assumption checks and main analysis at the same time. So for this analysis, you go to Analyze, you find the regression types of analysis. Then you go to Linear because we're interested in linear regression analysis. And here the labels of these boxes are very clear. So dependence means that our dependent variables, obviously, that we only can have one dependent variable for each run of analysis. And we have two independent variables here that we can see the label is very clear in SPSS. So that means that independent variables that also we can call it, like in some statistical textbooks, they may use the term predictors for independent variables, or they may use the term outcome variable for dependent variable. So they are pretty much the same terminology in the context of regression analysis. So this is enough, like you don't need to change anything else for this window of your settings. However, we still need to change some settings for analysis options to make sure that we have a comprehensive view of our outputs, and also to check our assumptions for assumptions of regression analysis. So first we go to statistics. So you see that some options are already ticked, but it can be different, the default setting based on the version of the SPSS that you are using. So just make sure that estimates is ticked, model fit is ticked. R-squared change is not very applicable for this type of analysis, but I will explain in other tutorial videos when it's applicable. Like for example, for hierarchical regression, that can be an important statistic. You can also, it's optional, you can tick a descriptive statistic if you don't want to check your mean and standard deviation separately. So it can gives you that information in the same output. And another one is collinearity diagnosis, this is for to check the assumption of multicollinearity. So that's important that you tick this option as well. The other one is Durbin-Watson that can gives you the one of the assessment of the assumption of independence, or that can be also important to check before interpreting the results of your regression analysis. And also you may want to tick case-wise diagnostics that can show you the outliers that can be like 3 standard deviations above or below the average scores for each variable. However, these are not, it doesn't mean that you necessarily need to remove that. So there is another measure of outlier that can show you if your outliers are influential, if they can be significantly impacting your regression model. And in that case, you want to decide to remove them. So here is everything is okay. Just make sure you have ticked all of these options and then continue. Then in plots, we need to have set some settings to make sure that we can check some further assumptions. So the first one is axis y and x that we put the z scores for residuals in y-axis, and we put the z-scores for predicted values in x-axis. So this is helpful, this setting. Just remember y is z receipt, x is z predict. This can help you to check the assumptions of linearity and homoscedasticity at the same time. Another one is for the assumption of normality of residuals, that you tick on histogram and normal probability plot, that it can gives you both of the figures, or both of the plots can help you to check the assumption of normality of residuals. And this is good enough, and you can click continue. And the last part that you want to set is what we call Cook's distance. That, remember, just uh, I just show you how to check that. You click on save, and here you find Cook's distance. And you tick this. This can show you if your outlier, if there is any outlier, it can shows you if there are influential outliers or there are outliers that you can keep and they don't have any bad influence on your regression models. And I will explain shortly how to interpret that. So you tick on that and continue. Click on continue, and everything is now good for running your multiple regression analysis. So we click on OK. So as you can see in your output, you can first see like some basic descriptive statistics like mean and standard deviation for each variable, for your dependent variables, for your independent variables as well. That is independent variable 1, independent variable 2. And also this can show you also the correlation, like bivariate correlations between based on Pearson correlations between your variables. However, it doesn't give you a very nice view of correlation. So you may want to check your correlations from the correlation analysis separately. I will cover how to the considerations that you need to check before running bivariate correlations in another tutorial videos. So I skip this one now because it can be the topic of our other tutorial video. But before going to the main results of your linear regression analysis, it's better to check the assumptions first, because if the assumptions are significantly violated, you cannot interpret the results of your regression analysis. There may not be valid or robust results to interpret. So I show you how to interpret your assumptions first and how to find them in your output. So the first one is the Dubin-Watson statistic that you can find it in model summary. So it has a very easy interpretation. As long as your Dubin-Watson statistic is very close to the value of 2, that means that your assumption of independence is met. It's actually one of the ways that you can check the assumption of independence. There are other ways as well. So here you can see that my value is close to 2. It's not very different. Like, for example, it's not 5. It's not like, for example, close to 0. So it's still very close to 2. So that means that I can say that this assumption is met, the assumption of independence. The other assumption that you can check is collinearity, that we call it multicollinearity. That means that your independent variables or your predictors are not too much correlated. with each other. So you can check it either with tolerance or VIF, but I would recommend check it based on VIF because it's a more lenient measure to check these assumptions. So as long as your VIF value is less than 10, that means that you don't have any concern with collinearity. That means that we can say that the assumption of lack of multicollinearity is actually met. So here you can see the value is way below 10. It's 1 for each of my IDs, and that means that you can actually consider that it's in a proper level. So the next part of the assumption checks the statistics that you can see is the Cook's distance, like checking for outliers, influential outliers actually. You can check your influential outliers in this table, residual statistics, and you specifically can search for Cook's distance. You can also check it with other statistics like Mahalanobis distance as well, but I would recommend Cook's distance. It's simpler to interpret, and also is very common to interpret the outlier assumptions based on this statistic for regression analysis. So for Cook's distance, you first find the row for Cook's distance, and you check the maximum column for that. So as long as the maximum value for Cook's distance is less than 1, that means that you don't have any participants showing influential outliers. That means that even if you find some outliers, like based on your descriptive statistics, as long as the maximum value for coexistence is less than 1, that means that you don't have any participants that affecting your regression models because of being an outlier. So for this result, I can see that my coexistence is way below 1. So because it's 0.14, so I can say that the assumption of a lack of influential outliers also is met. And also I wanted to show you that when you run coexistence SPSS, automatically you can have a column here that show that the coexistence value for each participant. It can help you for the situations that you have, like imagine that here, if I had coexistence more than 1, I could come here and see which participant showed that problematic coexistence. So we can see that coexistence is presented for each participants here, although I know some missing values, if participants have missing values, definitely so they are not included here. But for participants who have their complete data, you can see, you can find the coexistence here. And but here we don't need to do anything because coexistence, the maximum value is less than 1. That means that we have no participants with problematic outlier uh, statistics. And the next part and the last part that you can check for your assumptions is the assumption of normality of residuals. That these two plots can help you to check the assumption of normality of residuals. You should be familiar with this histogram plot. So that obviously it shows that the normality of, and remember that this is about normality of residuals, not normality of raw data, not normal distribution of your individual variables. So it's about normality of residuals in the context of your regression model, not individual variables. And you see that the residuals have a little bit, showing a little bit of a skewness because you see the histogram does not show a perfectly normal distribution for the residuals. And you can further check it here as well. So if it was a perfectly normal plot, you would expect that these data points would be very close to this line. But you see that some data points are a little bit away from the line. So we can say that the normality of residual assumption is not met properly. So you may want to consider some measures like transformation that I will explain in another tutorial video, what you can do in such situations. So the normality of residuals is not very okay. So the next plot that you can use to check your assumptions is this scatter plot. This scatter plot can be used actually to check two assumptions at the same time. The first assumption is linearity. As long as these data points do not shape a U shape, like either a U shape like this or a converted U shape like that, that means that the assumption of normality is probably okay and is probably met. That means that your predictors have a linear relationship with your dependent variable. And however, if these data points would be like a U-shape or converted U-shape, that would means that there are concerns with the linearity assumption. And but remember that this is not the only way. This is the most lenient way to interpret the assumption of linearity. If you want to have some more strict check on the assumption of linearity, you may want to run some scatter plots for your bivariate correlations. For example, you go to graph, you go to legacy dialog, you choose a scatter plot, simple scatter plot, define. And for example, I want to see that if my first independent variable have a linear relationship with my dependent variable, so I put it here, okay. And here, for example, it shows that it's probably a negative correlation, but this way, this plot does not show a perfect linearity because for a perfect linearity, if you consider a line here like this, you expect that the data points are very close to the line. So it can roughly show that it's a negative correlation, but you see that the data points can be away from the line. But it is actually not necessarily showing that you have a significant violation from assumption of linearity. That's just because the correlation is not very strong. The plot can show that the data are very fragmented or not very focused around the line. So that's why I would recommend that you check the assumption of linearity based on this scatter plot. As long as you don't see a U shape, you can say that this is the linearity is met because the scatter plots using this function, using the graph, usually does not show you a very nice plot, and so can be very strict in checking this assumption. So anyway, if you want a linear approach, you can check this linearity based on this plot, based on the interpretation that I mentioned. And the second assumption that you can check based on this scatter plot is the assumption of homoscedasticity. Uh, you don't need even to explain what does it mean in your reports, but homoscedasticity in a very simple language means that there are not any weird variances in your predicting between your predictors and your outcome variable. So homoscedasticity, you can say that it is met as long as your data points wouldn't shape a cone shape in your result. For example, I cannot see in these data points like a cone shapes like this, like a triangle or cone shapes like this, or maybe the opposite way, the cone shape like this. You can see that the data points are distributed evenly, first evenly, like if I assume a line next to zero, you can see that the data points are evenly distributed above and below this line. And also you can see that they are evenly distributed in different parts of the plot. So they are not like focused on a very specific part of my plot. So that means that the assumption of homoscedasticity is met as well. So as you could see, most of the assumptions are met except for normality of residuals. So still, if I want to be lenient, I can say that this is not a big concern with my assumptions because most of them are met, and the assumption of normality of residuals is usually violated in especially large sample, although we don't have large sample here, but for now we can just ignore that, just go with the main analysis. But if you want to be very precise, you can check the other video about how to deal with assumption checks or rectify the assumption violations um, in such situations. So, but we assuming that our assumptions are okay or good enough to go ahead with the main analysis. So the first part in the linear regression analysis that you want to report is this table, and especially the R square in this table. So R square can means that how much your all predictors, like the both predictors here together, can predict your outcome variable. For example, if your R squared is 0.17, that means that your both predictors together can explain 17% of the variance of your dependent variable. However, you cannot still say that you cannot have this interpretation for sure unless you make sure that this is significant. How you can check if your R square is significant? This is based on the ANOVA test. So ANOVA test is just for the significance of your R squared. So as long as the F statistics is significant, like that means that it's less than 0.05, you can say that your R squared is significant. So in this case, we can now with confidence have this interpretation that 17% of our dependent variable is explained based on all our predictors, that we have two predictors in this model, as you can see. You can have IV1 and IV2. So they both together can explain 17% of our dependent variable. So how about now if I want to see the individual contribution of each of my predictor? Like I want to see how much my IV predict the independent variable and how much my IV2 predict the dependent variable. I also want to see that the direction of the variables because here I cannot see the direction. I can just see the amount of contribution. So that's why this coefficient table can show you the direction of prediction for each independent variable and also the amount of their contribution to this prediction. For example, for IV1, you can either check on a standardized coefficient or a standardized coefficient, but we usually report them together. Because the standardized coefficient, and they are the same. I mean, the p-value that you can see here applies to both of them. But the standardized coefficient can help you to interpret the effect sizes. That's the only difference. For example, here for my first independent variable, I check the direction. The direction shows that this is a negative prediction. That means that the higher levels of IV1 is associated with lower levels of my DV. So that is an inverse prediction or a negative prediction. However, this is the opposite. For my IV2, the direction is positive. That means that the higher levels of my IV2 can predict the higher levels of my DV. So that is a direct prediction, or that is actually a positive prediction and a better term. However, so this is what the direction of my prediction means. But I don't know whether it is significant or not. For the significance of each coefficient, I need to check the significance of the t-value. And also I need to report the t-value. But this is the t and significant here is just to check if the coefficient for these uh, predictors are significant or not. So as long as the sig value is less than 0.05, I can say that these coefficients are significant. And you can see that both of them are less than 0.05. So that means that I can confidently say that both of my IVs have a significant individual contribution to predicting my DV. However, my first IV predict my DV in a negative way, and my second IV predicts significantly my DV in a positive way. You can also interpret the magnitude of the effects based on this beta coefficient. For example, as long as your beta is less than 0.30, that means that you have a small effect. So I can say that, so both of my IVs can predict my DV, but they have a small effect size based on the Cohen's guidelines. If you'd like support with writing up the results and interpretation for this analysis in your research paper, thesis, or assignment, feel free to book a proofreading session using the link in the channel description.